Hello, and welcome to this session at the AM Medical Summit. My name is Carlos Gonzalez with ASME's Mechanical Engineering Magazine. During the session, please use the chat box to enter questions and interact with other audience members. We will answer as many questions as possible at the end of the presentation. Please join me in welcoming our speaker, Dr. Daniel Porter. Currently, he is a regulatory scientist at the US FDA's Division of Applied Mechanics, researching the properties of additively manufactured lattice structures. Dr. Porter also has experience as a lead reviewer in the Office of Orthopedic Devices within the Center of Devices and Radiologic Health at the US FDA. He holds a Bachelor, a Master of Science, and a PhD in Mechanical Engineering from the University of Louisville. He completed his postdoctoral position at the Southern Methodist University in Dallas, Texas. Daniel, the session is yours.
Thank you, Carlos. And I'd like to add my primary function is to provide regulatory consults to lead reviewers and to perform regulatory research. And as Carlos said, today I will be discussing some of our research into additively manufactured lattices and porous structures. Before I start, I've got to read off a mandatory disclaimer. The mention of commercial products, their sources, or their use in connection with materials reported herein is not to be construed as either an actual or implied endorsement of such products by the Department of Health and Human Services. So a brief outline for my talk. I'll go into an introduction of lattices and their uses in the medical device area. I'll discuss motivation detailing why we're interested in this area of research. I'll give a bird's eye view of the general primary aims that we would like to address for this project. I'll discuss methods used to conduct our research herein, and then we'll go over some results obtained from the research methods. I'll finish with summary and conclusions from this, our scope and the results, and if I have some time at the end, I'll discuss some of our current and future works with respect to research in this area. So, quick introduction. Lattices can be seen as complex structures that may be fabricated using additive manufacturing. So what are they used for in medical devices? Well, lattice and porous structures are used in medical devices for proposed benefits such as compliance matching, such as attempting to match the mechanical modulus of nearby supporting bone structures to try to lessen, say, stress shielding. You can also apply these structures to the surface of lattices. You can put them on the outside of a lattice, and I'll show an image of kind of a little mock device we have so you can get an idea of how that happens. You can also create a bulk lattice solid, so you can kind of think of it as a deep lattice structure, or you can have internal lattices which are surrounded by a solid shell, and these all can be used for different functions or proposed benefits. And an example, here I have taken an image from literature of a hip system. And one of the components in the hip system is an acetabular shell, such as the one we've kind of rendered here. And what happens is this device goes into the acetabulum. This one that we've kind of rendered in-house has a lattice structure on the surface, and the idea is that skin and bone will grow into that lattice structure and anchor or have a biological fixation for that device. So when it comes to the number of input parameters that go into designing and even fabricating lattice structures, it gets a bit overwhelming. There are a lot of options, and this kind of slide right here is just to show you kind of the breadth of some of the lattice structures you can choose. And these are just the cell types. We're not going into like strut diameters or grading the strut sizes and things like that. So it's pretty broad. So why are we doing this research in this area? Well, there have been reports of device failures that incorporate lattice structures. From our previous review of cataloging AM metrics of cleared devices, a lot of devices that are additively manufactured have porous structures. And I'll show you a figure here in a second. We want to know what kind of questions asked during review of such devices. A lot of what we do is evaluating engineering and technical rationales. Internally, we want to also kind of understand the feasibility and potentially the burden of accurately maybe simulating some of these lattices, such as like in an FEA. Understanding the issues and errors that may occur during the simulations might actually help us steer certain submissions in the right direction. Less time, time better well spent. And finally, we also would probably, at the end of this, like to create standards that might be useful to all stakeholders and build confidence that, say, a lattice structure has been built properly given a certain AM system, or maybe you can test the performance given a standardized type of coupon. Here's an image that I'm sure a lot of folks watching this are familiar with. We've published this back in 2018. This is kind of a graph of the AM metrics of cleared devices up through about 2016, I believe. And as you can see from this graph, if you look at the gray section, 67% of the devices at that time kind of incorporated a porous or lattice structure in the device. Specifically relating to this presentation, some project aims is we want to understand, say, if a constant relative density, or porosity, if you will give similar performance given a certain lattice design. If performance changes, then at what range of inputs may be concerned? So we kind of would like to know that. When you numerically simulate a lattice, such as an FEA, how feasible is it to use data obtained from, say, large bulk samples or literature where they test standardized, say, dog bone samples? And then if you were to compare experimental and numerical simulations, what kind of errors would you get if you just did a general FEA, making general assumptions that a lot of people do? Here's a plot giving an overview of the broad situation. If we were have a design performance that we're trying to aim for, then simulation may, under certain circumstances, show consistent results over a broad range of design input parameters. However, if you experimentally tested some of those designs, performance may degrade at chosen design input levels. And so a design parameter could be reaction load, or maybe it's stress. And then maybe a design parameter that you can vary is strut size. So you can maintain a porosity by just having many different types of strut sizes. So that's kind of the idea. And this is just a quick little example of what that error could be. So the difference between the simulated and your experimental results that you actually obtain on the bench. More specifically for this project is we want to assess the effect of lattice design on mechanical response for some lattice coupons. We're going to do that by testing static tension, compression, and shear. And the outputs are going to be force and displacement. We're going to start with an AM system we have in-house, which can do nylon. And then we're going to, in the future, fabricate these samples in titanium alloy. And then back out and compare trends to see if what we found in nylon holds true for the titanium, or if things changed a little bit. Here's a graph of, well, essentially what we backed out with some preliminary experiments we did quite a while ago. And so what this is showing is reaction force versus displacement. And say you did an FEA on a bunch of different designs that had the same relative density, same cell type. So you took bulk material properties, you put an FEA, and you simulated a bunch of graphs. What we found is generally the simulation overlaps. They all show the same performance. But if you actually took those designs, printed them out, and tested them on a load frame, what we found was that decreasing strut diameter actually gave kind of degraded performance, and it was different from what we initially had simulated. So we're going into this research. So I'll kind of go through the methods and the samples and some of the results. What lattices to pick? There's a lot of lattices to pick from. We had to kind of select two. So we chose two lattices that we agreed on internally, and they were chosen due to their moderate simplicity to design and also to fabricate. We picked a regular repeating primitive body-centered cubic, or BCC as we call it. We also picked a stochastic lattice, which is designed using a Voronoi tessellation method, or VTM, and that's the one down there on the right. Each of our lattice samples is 20 by 20 by 20 millimeters. We have two different relative densities, 0.2 and 0.3. And within each one of those relative densities, we adjust 3 different strut diameters while maintaining that relative density. So the cell length and the strut diameters vary just to maintain those relative densities. What type of loading modalities are we doing? We're doing, as I said, tension, compression, and shear. So this gives you an idea of what our full samples look like and the grips attached to the lattice samples. And the software used to design and create these samples are ANSYS, primarily space claim from ANSYS, NTOP and topology elements, SolidWorks, and Materialize Magics. This is an image of a digital image of the samples and the various lattices that go into them, just to kind of give you an idea of how they change as the relative densities and the strut diameters change and such. So you can kind of see we have many different permutations. This doesn't even show the shear samples though. All right, moving on to simulation methods. We did all our simulations, or FEA simulations in ANSYS. Models from the design software were imported and processed from parasolids. And the FEA used a static structural setup with material properties that are derived from a bulk bigger device, so a cylindrical dog bone sample. The model incorporates plasticity, so we have a meso table that we incorporate into ANSYS. It also has the large displacement option, so there's an inherent geometric nonlinearity in the model. We also are using 3D quadratic elements. And here's a quick overview of the material properties that we input. Don't show the meso table for simplicity. We chose our worst case CAD setup for the model, which was the Voronoi model with the smallest struts, and we checked to make sure that the mesh converged within 5% on our quantity of interest, which was the reaction force on the model. We also checked, since these models comprise of 3 different bodies, the top and bottom grips and the lattice sample, we checked the effect of the bonded contact interface to see if that would change if we refine the mesh on the grips, and it actually only changed about 0.25%, so we deemed that negligible. As I said, our quantity of interest is force, and our outputs for the FEA are going to be force and displacement, or reaction force and displacement. So FEAs have boundary conditions, and so let's talk about those. For the compression samples, we completely fixed the bottom surface, and on the top we applied a 2 millimeter displacement. We restrained the planar movement on the top of the face. The tension samples were nearly the same, except we actually fixed a cylindrical surface on the bottom and applied a displacement to the cylindrical surface on the top. And the shear samples were similar to the compression samples, constraining the planar movement on top. Later on, I will discuss why we think that assumption was reasonable when I show you some images of the experiments. So I'll go into that at that time. The experimental method section's actually quite simple. So we fabricate and print all of our lattice samples. We're going to test 5 from each lot. We're going to take them to a servo hydraulic load frame, and we're going to test in compression, shear, and tension. And the pneumatic actuator moves at 5 millimeters per minute. We use a 15 kilonewton load cell, and we record axial load and actuator displacement. We obtain the data. We do take images of some of the failure surfaces and the failure modes using a high resolution microscope. I won't go into too many of those images due to time. Okay, so now we'll go into kind of the results section. So from the simulation, all the results were obtained and analyzed. You'll note that symmetry was not used in these simulations, but from what I can say up front is it may be appropriate under certain setups, so certain lattice types, loading modes, and failure modalities. These are images of the displacement, but we also catalog stresses for future review. And these are the results in kind of graphical form. This is kind of the more interesting part. So quick setup for this. The legend up in the top left, circles are the smallest strut diameters, diamonds are the middle range strut diameters, and triangles are the largest strut diameters. Y on these graphs is the load, X is the displacement, and the majority of these plots go out to about 2 millimeters of displacement. Dashed lines are the Voronoi or stochastic lattices, and the solid black lines are the BCC or the body-centered cubic lattices. What you'll notice for tension, which is what we're showing here, that the simulation results show that they relatively give the same performance. The Voronoi is technically different in design for every time you generate a new design, so that may explain why we do get a little bit of difference here in the simulation results. Overall, tension, compression, and shear, we obtain pretty agreeable performance for a loading mode using a specific cell type at a given relative density. AKA, if you notice, like all these black lines, even though they have different strut diameters, they all perform roughly the same, with the note that the Voronoi are a little bit different. Some experimental results. We'll start off with some images. The two top rows are the BCC and the bottom are the Voronoi samples. This helps to show what kind of strut fidelities our AM system was able to reproduce given the choices that we have for our AM system. It should be noted, though, that the struts on the outside of the Voronoi samples are half struts. This was done to make sure that designs are simpler, also to make sure it's easier to incorporate the samples into the grips. Also to note that this may induce additional performance effects since all the struts are not necessarily the same diameter and may even introduce stress risers. Going into some experimental results, here's some time lapses of some of the samples as they're being loaded. This one is a compression sample with a BCC lattice. You'll notice that given the failure modality for this lattice, it's actually quite symmetric. But the Voronoi, due to its stochastic nature, the strut dimensions as they deform are not symmetric. And we're also kind of looking into this, what kind of choices could symmetry be appropriate for an FEA for, like, say, lattice performance, because having symmetry in a model actually saves a lot of time in processing. Here are some shear samples that we loaded. These are kind of interesting. You can note that one of the failure modes is almost a perfect vertical separation from the grip wall. This is not the only failure modality that we see, but it is one that we notice quite a bit. The Voronoi shear sample, as it's being loaded, has a different failure modality shown here. You kind of get tearing at the struts at the top left, and then a little bit at the bottom right area, which kind of shows that the weak points on these lattices kind of vary. Another thing to note is that from the time-lapse images before failure show that the lateral movement on the grips it seems to be negligible. So maybe that assumption of completely constraining the plane in the FEA was a reasonable assumption. It's one of those things where you have to kind of verify. So you can kind of see that from there. All right. So this is simulation and experimental stacked on the same plot. Same legend, circles are smallest strut diameters. And so what we're looking at here is going to be compression. Now note there's a lot of graphs due to the test matrix we have. So we're going to pick out some that we think are more interesting. So we're going to start with compression, and we're going to put simulation, that's the dark lines, and then experimental is the dashed lines. And you'll see that the experimental actually does diverge quite a bit from the simulations. And so it's kind of an interesting assumption if you think that a constant relative density is going to give you the same performance, which might not hold true. So if we go from relative density of 0.2 to 0.3, you see it just kind of amplifies the effects for the BCC lattices. When we go to compression for the Voronoi, you see that the experimental performance generally shows the same at a relative density of 0.2. That's lower than the simulations. What we found that was interesting for this, though, is when we actually jumped up to a relative density of 0.3 for these Voronoi, which are stochastic lattices, this happened. So the smallest strut diameters actually increased their stiffness. And I guess I should kind of throw in that this is when the pores of the lattice are the smallest. For this design selection, the smallest strut diameter had just over the required pore size to facilitate powder removal in the general situation, given our system setup choices such as powder mixing ratio and things like that. The Voronoi is a stochastic structure and eventually leads to blind crevices, which makes powder removal and verification of residual powder difficult. Additional powder actually could reinforce the lattice sample and affect the compression modality given a stiffer mechanical response. This information is interesting because it may need to be considered if we ever go and design a test standard. So you have to kind of consider how feasible it is to remove powder from a sample that you're going to create and test. And the general conclusions are that the difference in simulation and experimental, or the kind of error you get, seems to increase as the strut diameter decreases. The Voronoi generally showed this same trend in compression, except when we kind of got into potential powder removal issues. This is kind of the same plot setup, except we're showing the shear modality here. You'll notice that the loading for these, the simulation and the experimental, is about the same. The simulations kind of all overlap. The experimental definitely has an error when compared to the simulation, and as you use smaller strut diameters, the increase in that error goes up, or the error increases as you go down in strut diameter. I kept the y-axis the same ranges on these graphs so that it's easy for you guys as the audience to compare, though this make it a bit difficult to verify the trends. So same kind of outcome. Lastly, for the simulation and experimental, we have the Voronoi at a relative density of 0.2, and I'm showing you tension and compression here. And what I want to show is that one trend you may get for compression modality, you might not get for the tension. So you see here the tension, the two largest diameter struts, given the same relative density, kind of perform within the same bounds. And it was only when we moved to the smaller strut diameter did the stiffness really kind of fall off. But I should note that even though there is a small discrepancy in the VTM simulation results, as you show from simulation, right? They don't exactly overlap. The experimental results are still much lower. So I'll go into summary and conclusions. The FEA simulation with bulk solid material property inputs all showed reasonable agreement for the regular BCC and generally for the VTM structures, given a constant relative density when taking into account what we're testing, which is the reaction load and displacement response. And that's shown in the graph in the top right. So you see the simulations all kind of line up and perform the same, even when you adjust the strut diameter. Experimental results, though, so experimental simulation response showed non-negligible difference at a given constant relative density. And as the strut diameter decreased, we had an increasing divergence from the simulation response. And that's kind of shown in the graph in the bottom right here. So simulation lines up, and then the experimental struts get smaller, they start to fall off. And so we kind of end with using bulk solid material properties for simulating lattice responses may not necessarily give you accurate estimates of experimental responses. Other considerations may need to be implemented if you want to kind of get an accurate simulation. You probably need some decent validation activities involved. So I'll quickly go into current works. So we're going to repeat kind of the same experiments we are currently and in the future. We're going to actually print these lattice specimens in a tie alloy using an e-beam machine. We're going to test them in the as printed and hipped condition. We're probably not going to do tension tests on these. We're probably going to substitute for some fatigue tests. So we're going to do some fatigue compression on some of these samples. And here's just a quick taste of what we're doing now. We don't have a lot of these samples. It's just a kind of preliminary experiment. So we've got some tie alloy samples that we're testing in the as printed condition. The smallest strut diameters show a lot of splintering, and then we increase the strut diameters. You kind of get this shear failure mode that you see a lot in literature. And here's some load displacement graphs. Keep in mind, an N of 1, we haven't tested multiple. And you generally kind of see the same performance trend, except it's not as amplified as we saw on the nylon. So we haven't simulated these are all experimental, but the smaller strut diameter just performed under the two larger strut diameters at the relative density of 0.3 in compression. Now, when we actually reduce the relative density, so we're using the smallest strut diameters now compared to the top left graph, it is actually the smallest strut diameters that were way stiffer than the two larger strut diameters, which is very interesting for us. And so we're going to look into this and see why that may be, because these are some considerations we might have to take into account when creating standards. Other future endeavors, quantifying error between the simulations. Right now, we haven't really quantified the absolute difference in those errors. Dr. Palepu is doing some spine cage impaction studies on mock spine devices that have lattice structures. We're also testing input process parameters such as laser speed and laser power on some of these metrics that we're looking at right now. So that's ongoing. And to end, I'd like to thank all the people at the FDA that kind of help and make this happen. I can't do this all myself. So we've got some lead reviewers, some ORISE students that help us, and some other colleagues in-house. And definitely the funding helps make this happen. I'd also like to thank Peter Kuris at Walter Reed for actually printing our titanium samples. And thank you for attention. I'll take any questions. If you have any questions on additive manufacturing from the FDA, you can email us at additivemanufacturing@fda.hhs.gov.
Thank you, Daniel. Let's jump to the Q&A. If you haven't done so yet, please enter your questions in the chat box.